Okay, good afternoon and welcome to the last session of the day. My name is Jussi Rahamäki. I'm chairing this session. Before getting started, I have a couple of housekeeping notes in case you haven't already heard today. So after the sessions, there's Augie Awards, which starts at 7 p.m. at the main stage in Mission City Ballroom. And after that, there is a after party at Glass House, San Jose, around 15 minutes away from here. And that starts from 8 p.m. and last until 11 p.m. There will be a shuttle service outside. And let me introduce the first speaker, Maria Korodova. She's assistant professor at Duke University, and she will let us know about research on enabling next generation Internet of Things and augmented reality deployment. So Maria, please go ahead.
Thanks for the introduction. So I'm absolutely delighted to be here to talk to you about our work on supporting next generation mobile augmented reality with the IoT. As introduced, I'm an assistant professor at Duke University. Before Duke, I was an associate research scholar and an associate director of a lab at Princeton. And before that, I did my PhD at Columbia. And in addition to my academic roles, I've had several years of industry experience in both strategy and technology roles. And some of the companies that I've had the pleasure of being affiliated with are shown on the screen. My Duke University lab works on enabling next generation mobile augmented reality, specifically on making next generation augmented reality both reliable and context aware. So we are building systems that adapt to the state of the environment and to the state of the user. And we are aiming to make them so reliable that you would trust your life to them, so that they would be suitable for health and safety critical applications. And towards this overall vision, we have multiple projects that address its multiple dimensions. So for instance, we work on improving coordination in multi-user augmented reality systems, on improving depth data processing, on making eye tracking more reliable, and solving some of the privacy challenges that are associated with it. And we are directly working on some applications that go towards more trustworthy AR. We are working on AR for surgery and on AR that provides safety and security guarantees. For instance, on AR applications that guarantee that holograms would not be moving, would be moving out of the way of important objects. Here, I will talk to you about the architecture that it's a pervasive paradigm where mobile AR is supported by the environment around it. So I'll talk about some of the limitations in mobile AR these days, especially in its environmental awareness. I'll talk about how edge computing works with mobile AR to address some of its limitations. And then I'll talk about how AR, IoT, and edge can work together to take AR to the next level. So mobile AR these days is already incredibly impressive. So it is truly able to merge the physical and the digital. And it enables experiences that are not possible with any other type of media as a result. A couple of examples of that my lab is working on where we are truly merging the physical and the digital are AR-assisted surgery and AR in an art gallery. In the surgical scenario, we are taking a preoperative scan of the patient, and we are overlaying that scan directly with the patient's in-surgeon's view. This allows the surgeon to directly target the part of the anatomy that he or she would like, without having to turn the head away and having to mentally reproject the scan. So it's the type of experience that truly relies on being able to merge the physical and the digital. In an art gallery, we are able to see that a user is engaging with a painting through eye tracking. And this allows us to produce holographic additions to the painting. So overlay holograms with a view of the real world around the user. And again, something that's not possible with any other technology. However, this mobile AR these days has a lot of limitations. And to merge physical and digital, you have to have a very good understanding of the physical. So you have to have a very good understanding of the state of the environment. And this is where there is lots of room for improvement in current AR. Currently, to be able to understand the world around an AR device is very resource intensive. And this is where AR devices make a lot of mistakes. You can think of those mistakes as belonging to two categories: semantic mistakes and spatial mistakes. Semantic mistakes are mistakes in understanding of the nature of the world around the device. So you do not see a sofa as a sofa, or you see a cat as a dog. And this leads to either incorrect interactions with the world, so you're not able to engage with the surface in the way that you would like, or it just leads to the generation of incorrect holograms outright. The other type of errors are spatial errors, and some of their examples are shown on the screen here. Those of you who have played with markerless AR have no doubt seen spatial errors. What's shown on the screen are scaling errors and positional errors. Scaling errors that are shown to the left of the screen are where, due to the erroneous depth mapping, a hologram that's generated is either too large or too small for the environment. So you see a chair that's gigantic and an echo show that's too small. And this is due strictly to the incorrect perception of depth, that the AR device here perceives the surface as being either closer or farther than it truly is. Example on the right is an example of drift, unintended holographic motion. This is a very typical situation in AR where we are placing a hologram in one place, and then as the user moves around and perhaps comes back to the place, the hologram is moving. And it could be moving a little bit, as is in the panel on the middle, or it can be moving dramatically, as is in the panel to the very right. We recently did a study where we quantified the extent of drift in modern platforms in multiple environments. And for many conditions, the expected drift right now is on the order of tens of centimeters, but many instances of drift that is so dramatic that it's unusable from the point of view of the experience, such as the example that's shown on the very right panel here. So overall, while mobile AR is already truly remarkably impressive, major improvements are required to make it reliable. One architecture that has been talked about for supporting mobile AR is edge computing. And this is where we place additional computing capabilities closer to the end devices. And we are using them to do some processing on behalf of the mobile device. You've heard about edge computing in some of the talks here. It's a paradigm that is used in many other modern applications as well, not just AR. It has its role in VR, in coordinating drones, and in video analytics, for instance. For AR specifically, it can be used for remote rendering, for coordinating multiple devices, and for running additional intelligence on behalf of mobile devices. It's very difficult to run some of the cutting-edge neural networks, for instance, directly on the mobile itself. So running it on the edge makes a lot of sense. Some of the examples that my lab has been working on are on the screen here. So we've been using Edge to do advanced neural network-based processing on behalf of mobile devices, for instance, for making depth data better, for depth data in painting, as is shown on the right of the screen. And we have also been using it for doing cognitive context detection. And this directly relates to the previous talk. This is where we are using eye patterns of the user to see whether the user is engaging with the world around them, if they are, let's say, reading, or if they're programming, or if they are talking to someone. And we use that information on the edge server to feed into a deep neural network, and we transmit this information back to the mobile device for adapting the state of the holographic experience. So this is a classical way of using edge computing, using edge to do the types of processing that's very hard to do on a mobile device itself. Unrelated to that, in a different field entirely, edge computing is actually used as a de facto standard for interfacing with IoT devices. So the vast majority of IoT deployments these days have a gateway or a server that is used to coordinate and manage the IoT devices, and in some cases run some intelligence on their behalf. So now we have this merging of two very interesting paradigms, that on one hand we have mobile AR devices and edge together, and on the other hand we have IoT and edge together as well. So the question is, can we make this system work end to end? Can we use AR to browse the IoT? And can we use IoT to help AR? And the answer to both of these questions is yes. Some of the ways that IoT can help AR include, for instance, additional environmental sensing. We can use smart cameras to augment the sensing that mobile AR cameras do to improve the sensing quality or to reduce resource consumption. We can also use environmental actuators such as smart lights, shades, or displays to optimize mobile AR experience. You can think of, for instance, turning on the light if you are perceiving the environment as being too dark for the mobile AR experience. Or you can think of lowering the shade if the environment has too much glare. So this paradigm is potentially very powerful since we're shifting the burden of environmental understanding and control from the mobile AR device and the user onto the infrastructure. Theoretically, we should be able to have an AR device do all of environmental understanding by itself. But it's very resource intensive and it takes a lot of time for the user. We can also theoretically have the user adjust the state of the environment him or herself. But there we are relying on the assumption that the user would be able to fully map the state of the environment to what's best for the mobile AR experience. And that is a very tall order. That would require the user to have an in-depth understanding of how localization and mapping works, that's very impractical to assume. So it was a potentially very powerful paradigm that converges IoT and AR. So I'll talk about some of my lab's work in this direction. Overall, the core connectivity between mobile AR and IoT can be readily established. It's very easy to hack it together with multiple platforms. Some examples that my lab has been playing with are shown on the screen here. To the left of the center is an example of an IoT-based e-ink display that shows a marker. And the marker that it shows is programmable, so you can change the state of the marker based on the state of the environment, or you can program the marker by the edge server. And the magic leap that is shown to be reading this marker would show different holograms depending on the state of the marker. So this is a full end-to-end correspondence of mobile AR and an IoT-based display. To the right of the center is an example of a smart light bulb that's connected to the edge server. And this light bulb changes its levels depending on the metrics that are captured by an AR app that is running over Google AR Core. So here you can imagine that the light would go on if AR Core measures the environment to be too dark, for instance. And to the very right of the picture, we have a Raspberry Pi camera that we mounted in our lab. This camera is surveying our lab constantly. It's taking pictures of the lab. It's sending them to the edge server for processing. On the edge server, we run various analytics on those images. And we then use the inputs from the edge server to adjust the algorithms and applications for the mobile AR devices that enter the lab. So overall, hacking together the IoT and AR is fairly straightforward. Where the challenges are is in making this more automatic. So for instance, being able to localize IoT devices precisely is quite challenging. You can hard code it, but being able to do it more automatically would be highly desirable. For lots of these applications, you would also want to map the states of environmental actuators to the states of the environment. So you would want to say that if I lower the shade by that much, that changes my light level by that much. And it's very difficult since environmental conditions change as well. So the extent of any actuator's action would be different in different times of day and different weather conditions, for instance. This is where some of the research challenges are, despite the connectivity being very straightforward. We've been playing quite a bit with this idea of having environmental cameras that are surveying the scene and that could help AR devices in obtaining semantic awareness specifically. One use of it could be to help provide an alternative view of the scene that a mobile AR device is seeing. And this can help with image recognition. So overall, image recognition enables seamless and contextual mobile AR. If I am looking at the surface and I immediately identify the surface as a table or a sofa, that helps me interact with it accordingly. This is usually done with deep neural networks. But the issue is that deep neural networks make a lot of mistakes. They get confused by objects in non-standard poses, by partially occluded objects, or partially occluded views of the mobile cameras. And they get confused by distortions as well. So if your mobile AR device captures images that are slightly blurry, that's problematic for image recognition. In this case, if we take multiple views of the scene, that could give us additional information to improve the quality of image recognition. An image to the right here hopefully gives some intuition for why that is. So here we have taken the exact same scene, a laptop and a helmet together, and we have captured it from two different views and ran it through the very same DNN. In one of these views, we only see a helmet, and on the other, we see both objects. So if we are able to intelligently combine this information, we should be able to do better in recognition than one of those views alone. So what we have done in our work is build an architecture where we take images that are taken from different views of the environment. We send them to the edge server for processing. We run image recognition DNNs on the edge, and we combine the results that are taken from these multiple views to improve the overall recognition. And the specific way that we do this is a machine learning-based approach that's called auxiliary-assisted multi-view learning. It essentially amounts to taking not only the results, but DNN's confidence in the results into account when making recognition decisions. And we have demonstrated that this improves overall recognition accuracy dramatically, particularly in cases where mobile devices captures are corrupted by, let's say, motion blur. This is one example of using stationary camera to help with semantic awareness. It's readily apparent that there could be others. So for instance, you could use your mobile AR device to provide awareness of one part of the space and the stationary cameras to provide awareness of others. You can also think of using stationary cameras to inform mobile AR devices of previous states of a space. So let's say if you are in a room that's empty currently, but that was very busy 10 minutes ago, this is something that perhaps your application could make use of, and this is what you could gain awareness of with these types of architectures. Another foundational challenge that my lab is working on is enabling this kind of automatic adjustment of environmental conditions for spatial awareness. And the issue is that to be able to do that right away, you need to be able to say that this specific set of conditions is associated with poor spatial awareness. And us as users, we learn it as we play with technology. So for instance, if you play with markerless AR, you'll develop a feel for featureless spaces being problematic. Or if you play with devices that have time-of-flight sensors, you'll develop a feel for dark surfaces being problematic. So in our ongoing work, we're building a system where we are taking various metrics of the environment, and we're building classifiers to map those metrics to poor spatial stability, to then be able to automatically change the state of the environment to improve the stability. So in summary, modern mobile AR is already truly impressive, but it has many limitations as well. So environmental awareness is where AR currently makes a lot of mistakes, and it's clear that there is lots of room for improvement. We've been working on one architecture that could potentially help. This is where we are taking environmental sensors and actuators, and we are using them to provide additional information for mobile AR systems or for adjusting the state of the environment to optimize mobile AR performance. And I've briefly touched upon several platforms and algorithms that we are building. And I'm happy to talk about these or others after the talk or offline. So I'd like to say thanks to wonderful research staff that's working towards this vision, a core group of students and postdocs, graduate students and postdocs that are shown on the left, and many, many undergrads, some of whom are shown on the right. And I would like to acknowledge generous support from National Science Foundation, North Carolina Lord Foundation, AWS, DARPA, Facebook, now Meta, and IBM. And I'll take questions now.
Thank you very much. Any questions from the audience?
Hi, Maria. Good talk. Thank you. Are you guys doing anything with kind of a pre-canned digital twin of a space and incorporating that into your research?
Yeah, that's a great question. So we are working on developing the right types of digital twins here, yes. So the problem is that I think that's a research problem on its own, how to get the right level of digital twin that's appropriate here. You have this issue that a typical space is typical space where you deploy AR experience is the so-called semi-static space, neither static nor dynamic. It's some parts of it change and some don't. So not all twins apply. And it's also that you want to capture properties of the space that are not captured by many existing digital twins. So for instance, for best rendering of for best holographic rendering, you want to know where the light sources are. And so you have to build twins that incorporate that. So I think overall, coming up with a best digital twin for these types of settings is a great research direction, and it's something that will definitely be worked on for the next several years.
Yeah, and okay.
Are you also either pursuing or interested in pursuing the kind of context awareness research that would be based on a much more heavily censored phone itself? All sensors double, triple the number, and different types beyond what's currently in a top-of-the-line phone. As those sensors become higher resolution, smaller footprint, and lower power drain, it seems like that's an extremely rich path going forward, at least. What are your thoughts?
So context awareness in general in applications, yes, definitely, absolutely, yeah. It's already clear that there are ways of adapting algorithms to space and experiences to the user. And there's definitely tons of potential for it, and definitely it's a rich space in its own.
And one more question.
Yeah, so my question is, so I'm Klaus from Nokia, and this is combining the infrastructure camera sensors with the mobile sensors.
Yep.
The challenge I see there is that you may have different models running on the mobile than you have in the infrastructure, and how do you see that? Do we need to standardize how we perceive the world, to extract the features, or what would be the way?
So, yeah, so that is one of the challenges here. You have heterogeneity in hardware and heterogeneity in sensors and heterogeneity in processing capabilities as well. So our current work takes, we take an edge-centric approach where we feed the data to the edge server, so the processing is uniform. So that doesn't get us past the question of hardware heterogeneity, but it does provide one place for the execution. Longer term, indeed, I think in all of this space we will have, we will build techniques where we have heterogeneous neural network architectures as well, where we have lower end architectures running on lower end devices with intelligent ways of merging the results with others.
Okay, let's thank the speaker again.